This webcast continues the discussion of the lab on how unbalanced forces affect acceleration. We are in part 1, experiment 1 of this lab, and at this point you should have completely filled in the table at step 9. So you should have 10 values of applied force and acceleration. Okay, so the next thing that we need to do is to graph this data and see, what it looks like. What is the trend when we graph acceleration versus net force? Now you can use this sheet of graph paper that's provided in the lab packet, but I'm going to graph mine in Microsoft Excel, and if you'd like to do that, you can follow along with me. So first I'm going to set up a data table. The independent variable goes on the left, and that is the net force, which is measured in newtons. The dependent variable, and I'm just going to make that column a little bit wider. The dependent variable is the acceleration, which is measured in meters per second, or meters per second squared. Okay. So I have my columns labeled. I'm going to type in the data. Let's see here. Okay, so I've got my data here, and so now I want to graph this. And so I'm just going to select the numerical values of my independent and dependent variables. I'm going to insert a scatter graph, and I'm just going to use the one that shows my data points. And so I can already tell this is a nice linear trend. It looks very nicely linear. I'm going to add axis titles, and let's put some nice labels on this. So the label above the graph is acceleration versus net force. My independent variable is the net force, so that goes on the x-axis, and my dependent variable is acceleration, so that goes on the y-axis. Okay, so we have a nice linear graph, and so I'm going to want to write a physics equation to represent this relationship, and that will just be the equation of this line. In order to write this equation, I'll have to find the slope. Now there are a few ways to do this, but since these data points are so straightforward, it's pretty clear that every single data point is on the line. I am going to just use 2 of these data points to find the slope. And so let's see here. So this is for experiment 1, which is acceleration versus net force. And I'm going to find the slope. It's going to be, just go back and look here. I'm going to use my second and last data points, or maybe I'll use the third and last. Okay, so I think I see what we've got to do here. So I've got 8 minus 2 and 400 minus 100. This was meters per second squared because this was acceleration and this was newtons. And so I get 6 divided by 300 meters per second squared per newton, and that is 0.02 meters per second squared per newton. That is the slope of this line. Okay, now I'm going to let you do steps 12, where you write a physics equation, and 13, where you explain the meaning of that slope on your own. but I do want to talk about how you would simplify the units of the slope. So because our graph was acceleration versus net force, the units on the y-axis were meters per second squared. The units on the x-axis were newtons. So these are the units of that slope. And I've given you a hint here. It says, remember that a newton has a dimension equal to a kilogram times a meter per second squared. So I'm going to replace newton with its dimension. And I can see that meters per second squared now was both on the top in the numerator and in the denominator of this fraction. And so I can cancel it out. And so in simplified form, the units of this slope are 1 over kilogram, the inverse of mass. Okay. The lab gives us some additional data. So we used a 50 kilogram mass, but here is the acceleration versus net force graph for 3 other amounts of mass. So you can see the key here, 130 kilograms, 170 kilograms, and 200 kilograms. You can see that all of these graphs are linear, but the slope is different depending on the amount of mass. The reason that I'm giving you these additional sets of data is because, we've done this before. When you want to try to understand the physical significance of a slope, it helps to replicate the experiment and use different values of the constants. So the most important constant in this experiment 1 was the amount of mass. And so I'm going to fill in my data. So I used 50 kilograms, and we just found a slope of 0.02. And then in these yellow cells are the data that was given in that table above. Now, we can tell that as the mass gets bigger, the slope of the acceleration versus net force graph gets smaller and smaller, but they clearly don't match. Since we found that the units, the simplified units of that slope are 1 over kilogram, I want to look at what is the inverse of the mass. So 1 over 50, look, it happens to equal 0.02. That matches the slope that we found. 1 over 130, I'm taking the inverse of the next one. Look, that's 0.0077. And if I do all of these, I'm going to see that the inverse of the mass matches the inverse, or matches the slope of that acceleration versus net force graph. And so we are going to be able to draw a conclusion about what that slope of the graph of acceleration versus net force means. So the slope of the acceleration versus net force graph equals the inverse of mass. It equals the inverse of the mass that was used in the experiment. The experiment was replicated 4 times with different amounts of mass, and in every case the slope of the acceleration versus net force graph equaled the inverse of the mass. Also, the units of the slope of acceleration versus net force simplify to be 1 over kilogram, which are the units of inverse mass. Okay, so we have two pieces of evidence that we need to cite. There's the fact that we repeated the experiment 4 times, and in every case, the value of slope that we found for this graph equaled the inverse of the mass. And then there's also the evidence that the units of the slope of that graph simplify to be 1 over kilogram, which would be the units of the inverse of mass.